Welcome back to the Mathematic Fanatic. Today we have an integral which can be done via partial fraction decomposition. Notice that the numerator is a fourth degree polynomial, while the denominator is a third degree polynomial. So that means before we can apply partial fraction decomposition, we must first divide the two polynomials. So now we're dividing the polynomial x to the 4 by the polynomial x cubed minus x squared plus x minus 1. Remember, it can be helpful to add all of these extra zero terms so that you can space things out by their degree. So we begin. X cubed times what is x to the 4? The answer is x. Now we multiply x by this entire polynomial, and we get x to the 4 minus x cubed plus x squared minus x, and then we subtract that entire polynomial from the original. So these terms cancel out, that should always happen. And then we get 0 minus negative x cubed, so that's positive x cubed. 0x squared minus x squared. 0 minus negative x, so that's plus x. And then we can just bring down the rest, plus 0. Now, we continue. X cubed times what is x cubed? Well, of course, that's 1 plus 1. Now we multiply 1 times that entire polynomial, we get x cubed minus x squared plus x minus 1, and then we subtract. Fortunately, most of these match up, so we just end up with 0 minus negative 1, and that's plus 1. Now we can go ahead and try again. X cubed times what equals 1, but we can see that the degree of what we have here is too small for that to work, so that means we're done, and that is our remainder. It's 1 over the original, the divisor. So that is our result. So that means our original integral can be replaced with this one, and integrating this term is easy, integrating this term is easy. We just have to integrate this term now. So now we're looking at the integral of 1 over x cubed minus x squared plus x minus 1. In other words, 1 over a third degree polynomial. So hopefully we can find a way to factor that third degree polynomial, and then we can apply partial fraction decomposition. So a good technique for factoring third degree polynomials is to try and look for groupings that will allow you to pull out a common factor from each group. So in this case, I can see that we have two similar looking groups here, right? We have a power of x minus the next power of x down in each of those groups. So from that first group, I can see we could pull out an x squared, and what is left would be an x minus 1. And then from that second group, I see we already have an x minus 1, which is exactly what we need to match with over here. So I can just pull out a 1 from that group, and I have successfully been left with the same factor from each group, which is exactly what you want, because then we can pull that out and create the factorization x squared plus 1 times x minus 1. So that is a factorization of that polynomial. I have factored this third degree polynomial into a second degree times a first degree. Now it would be super cool if we could factor this one further, but unfortunately this is a polynomial that cannot be factored. At least not if you're only using real numbers. If you open yourself up to the complex numbers, well then that can be factored as x plus I times x minus I. But if we're stuck with real numbers, then we have to conclude that that polynomial cannot be factored, unfortunately. So what does this mean for our partial fraction decomposition? Well, if we're allowed to use complex factors, then we can completely factor it like this. And then because all of those factors are first degree, the partial fractions technique guarantees the usual, that there's something over this plus something over this plus something over this. And if we could just find those right numbers a, b, and c, then we'll be able to break down this large fractional expression into the sum of those much smaller fractional expressions. But unfortunately, it only works like that if your factors are first degree. If we have the unfortunate situation where one of our factors is second degree, which we would have to deal with if we weren't allowed to break down into complex factors, if we have to keep this as x squared plus 1, which is a second degree polynomial, then the corresponding partial fractions format wouldn't simply be a number over x squared plus 1. If the denominator is quadratic or second degree, it's not quite that simple. Instead, the partial fractions technique guarantees that you can put that in the form ax plus b. So it's not simply a number over the denominator, it's a number times x plus a number over the denominator. And it's always like that if that denominator is second degree. Now again, if you are willing to open yourself up to the world of complex numbers, then this ugliness goes away. All polynomials are completely factorable down into first degree factors. That's the beauty of the complex numbers. That's called the fundamental theorem of algebra, that all polynomials can factor all the way. But if unfortunately you restrict your attention to the mere real numbers, then sometimes you have polynomials that can't be factored any further. And in that case, partial fractions gets just a little bit uglier, where your numerators in those cases have to be not just numbers, but themselves first degree polynomials, ax plus b. But anyway, the technique still guarantees that we can find numbers a, b, and c so that this decomposition is legitimate. And it's still at least true that this is an easier thing to integrate than this, so that's still a worthwhile trade. Let's see if we can find the right numbers a, b, and c. So we'll start by multiplying both sides by this entire denominator. So on the left side, we'll just get the number 1. The complete denominator cancels. On the right side, in the first term, the x squared plus 1 cancels, and we gain a factor of x minus 1. On the second term, the x minus 1 cancels, and we gain a factor of x squared plus 1. Now, there are a collection of techniques that you can use to find these values of a, b, and c. One technique is to completely expand the right-hand side and then compare coefficients. The coefficients on x squared and x and constants must be the same on both sides, so from that we can construct a system of equations for a, b, and c. That's perfectly cool, but that would be a system of 3 variables and 3 equations, which can be difficult to solve. So rather than rely entirely on that system of equations technique, I'm also going to throw in the technique where I let the value of x be a certain choice of number. And I'm going to choose the number 1. The reason I'm choosing the number 1 is because if x equals 1, then this is 0, so this whole term is 0, and then I get the much nicer equation 1 equals c times 1 squared plus 1. And that tells me that 1 equals c times 2, and that tells me that c equals 1/2. So immediately it gives me 1 of a, b, and c. I already know that c equals 1/2. So I don't have to deal with 3 variables anymore. Now I only have 2 left. And so even if I still have to deal with a system of equations, it's going to be a system of 2 equations now and 2 variables instead of 3 equations and 3 variables. Now, normally, perhaps if you're used to linear factors and linear denominators, then that trick will work for finding all of the variables. But unfortunately, it's not going to go like that this time, because you see there's nothing I can let x equal to cause this factor to be 0. That's because this is an unfactorable polynomial, at least in the real numbers, which is equivalent to saying there's nothing you can plug in to make that 0. And again, that's only if we allow real numbers. If you allow complex numbers, of course, you can plug in I. But if we don't have that, then there's nothing we can do to make that 0, so this trick is not going to work to turn that second term into 0. So now we will have to resort to expanding both sides out. I'll delete all this. I'll move this up here so we can remember. And I'll expand both sides out and then compare coefficients on both sides. So, foiling this out, we get ax squared minus ax plus bx minus b. And then distributing the next term as well, that's plus cx squared plus c. Now, fortunately, I already know the value of c. We already figured out that c is equal to 1/2. So that's definitely very helpful. But unfortunately, there's still two unknowns. So let me compare coefficients. We have x squared terms, we have x terms, and we have constant terms. So for the x squared terms, we can see that ax squared plus 1/2 x squared apparently equals 0x squared, since there's no x squared terms on the left-hand side. So we can simplify that down to just a plus 1/2 equals 0. And fortunately, that gives us the value of a. A must equal negative 1/2. Now we'll compare the x terms. The x terms say that negative ax plus bx, again on the left-hand side we have 0x terms, so that tells us that negative a plus b equals 0, and fortunately we already know the value of a, so that gives us negative 1/2, which is positive 1/2, and so that means b must equal negative 1/2. And then of course you can also use the constant terms, but at this point we have already found 3 variables, so we don't need to. But just to check it out, it tells us that 1 equals negative b plus 1/2. And that also agrees with this fact here. If b equals negative 1/2, then that says 1 equals 1/2 plus 1/2, and that's true. So again, if we hadn't done this trick here with c, where we plugged in x equals 1 and then got that value real quick, then we would have gotten more sophisticated equations here. And so doing that, it still would have been possible to solve that way, but doing that trick where you plug in the right x value first can definitely help simplify the system of equations that you're ending up with. In this case, it really wasn't much of a system at all, so that was pretty nice. Okay, so we have our values of a, b, and c, so let's pop those into our integral. So we're trying to perform this integral. We found out that the values of a, b, and c are negative 1/2, negative 1/2, and positive 1/2. So filling those in, we get the following. Now recall that fractions can be split up if their numerator is split into multiple terms. So this first fraction here, if we want to, and in this case we do, split it up as follows. That's negative 1/2 x over x squared plus 1 plus another negative 1/2 x, negative 1/2 over x squared plus 1. And I wrote it like that, but certainly you could also write it as minus like that. And then plus 1/2 over x minus 1. So the reason we want to split it up like this is because it's really 3 separate integrals. Let's write it out as 3 separate integrals. We have negative 1/2 x over x squared plus 1. We have another negative 1/2 1 over x squared plus 1. And then finally we have 1/2 over 1 over x minus 1. So we have 3 different integrals now, and each one will require a different technique. Let's go ahead and start with this integral here. Okay, so for this integral, we have a second degree polynomial on the bottom and just an x on the top. Now that's perfect for a u substitution, because if I let my new variable u equal that denominator, well then that means my du is pretty much my numerator. Now I say pretty much because we're missing the 2, but if you're missing a constant, that's never a problem. You can always do the following. Just toss in an extra 2 here, as long as you toss a 1/2 outside, and that's the same thing. So I'm looking at the integral of 1 over u du. So this is the integral of, or 1/2 the integral of 1 over u du. And of course that is the natural log of the absolute value of u plus c, but we'll worry about the plus c's at the end. And so we just have to put back our u. That's 1/2 natural log of x squared plus 1. Now it's good to put the absolute value on natural log, but sometimes if you want to, you can inspect what's on the inside and notice that that's always going to be positive, right? Because if you square something and then you add 1, well, squaring always makes something positive, and then adding 1 is just going to keep it positive. So there's no way that thing on the inside is going to be a negative. So if you want to, you can replace those absolute values with just parentheses, because they're never going to be necessary, because that inside thing will never be negative. Not important, but some people like to do that when they can. Okay, so that's our first integral. So for this integral, the same u substitution isn't going to work because we need an x in the denominator for our du, and we don't have it. So we'll have to try a different technique. In this case, the right technique is a trig substitution, and the clue to that is that we're dealing with an x squared plus something, and we don't have anything upstairs to be our du. So we'd always prefer to use a u substitution, but that's not going to work. So the next thing to try is a trig substitution. And the right thing to try here is x equals tangent. The reason for that is because we have the wonderful relation tan squared plus 1 equals secant squared. And after we make the substitution, that's exactly what's in our denominator, tan squared plus 1, so we can replace that with secant squared. That's especially helpful because our dx, the derivative of tangent, is secant squared. So once we do our substitution here, we're going to end up with, that's 1 over tan squared plus 1, which is secant squared. And then dx is secant squared. So those two things cancel. We're just looking at the integral of, the integral of 1 d theta. And of course that's theta. And what is theta? Well, if x equals tan of theta, then theta itself must be the inverse tan or the arctan of x. And of course, for that integral alone, you should put plus c. But since we're doing this as a collection of different integrals, we'll just save that till the end. And then finally, integral number 3 is just 1 over x minus 1. And of course, the integral of that is simply the natural log of absolute value, x minus 1. Plus c, but we won't worry about that. So putting this all together, we have negative 1/2 times positive 1/2 times the natural log of x squared plus 1. Remember, you can drop the absolute values if you want, but you don't have to. Minus 1/2 times arctan of x plus 1/2 times the natural log of absolute value x minus 1. This time we can't drop the absolute values because this certainly could be negative for some values of x. Okay, so that is the final form of just this. And then don't forget, we still have those 2 extra terms from back when we did the long division. So that means our final answer is 1/2 x squared plus x plus all of that. And then don't forget, plus c. So quite a long expression. 1/2 x squared plus x minus 1/4 natural log absolute value of x squared plus 1 minus 1/2 arctan x plus 1/2 ln of x minus 1 plus c. So quite a mouthful, but there you have it. I hope all of those steps made sense, and catch you in the next one. Take care.